In this section, we're going to look at an alternative way of looking at points on a coordinate system. We're going to be using polar coordinates. The objectives we have here is we want to be able to plot points using polar coordinates, to convert between both of them, so to take a XY point on the rectangular system and convert it to polar and vice versa. And then we're going to also look at how equations will look different in their rectangular and polar forms. One of the benefits of having this alternative way of looking at things is that equations, which would be complicated to describe using X and Y, can actually be vastly simplified by using this other form. So in the polar coordinate system, just like we have done a lot in this section, we're going to draw we're going to have a horizontal ray, kind of our starting ray. That's going to be our polar axis, and it's going to be in the XY coordinate plane. So we have a kind of a starting point, and the end point is going to be our pole, which would be like our point. A point P in the plane is described by two things. And so we write these things kind of like an ordered pair, but we have different places. We have R, which is going to be, if you'll remember, the radius of the line, the length of the line, and then theta is the angle from which we left from the original horizontal ray. Obviously easier to look at with a picture. This figure plots the point PR theta in the polar coordinate system, where R is the directed distance from the pole O to the point P. And theta is going to be the angle from the polar axis to the lag segment OP. So we have an endpoint here. This is our point P, described by the angle at which we left our polar axis. That's our theta. And then from our pole to our point P, we have the distance R, which would be, as we can see, this is going to give us a rectangle. We can describe it in terms, you can think of it as like our radius. Now, the polar coordinates of our point, unfortunately, are not unique. If we have, like, for example, a point like 3, 4, this is a unique place, and that gave me a really fat, I'm going to make these a little bit smaller. Give me a fat point that's supposed to be 3, 4 there. That's a unique place on the XY coordinate system. There's no other way for me to get to that point except by going 3 to the right and 4 up, right? That's the traditional way that we've looked at it. But as we've seen with polar, with rays and moving angles, the ray is just going to go in a circle, so there are infinite number of ways we can express and end up at the same point. The polar coordinates 360 and then 3, 420 are going to end us in the same spot, as will 3, negative 300. 420 is just 360 more than 60 degrees. And then negative 300 is just going in the opposite direction. So there's lots of different ways for us to express any point on the rectangular coordinate system. In general, if a point has polar coordinates r theta, then for any integer n, integers are our positive and negative whole numbers, if I multiply that theta by 360, n equal to 0 times, n equal to 1 time, 2 times, negative 1, we can have all kinds of different points there. We can also express them in radian measurement, as you guys know. Now, when r is negative, now we have to interpret that and give it a meaning. We define r as a directed distance. So if r is negative, the point is r units on the extension of the terminal side. So we're going to extend that terminal side in the opposite direction, and our terminal side is simply where, our theta is ending up, right? So let's take a look at this kind of visually. I think this will help. So here we have a point, -4, -30. So the -30, as you know, takes us in a direction. -30 would take us from our starting side here all the way down to our terminal side. And if this had been a +4, we would have ended up 4 units away from that point. Or from O, right? Our starting point of origin here. If it's negative, however, we're going to extend what it would be 180 degrees such that this is a straight line, and we're going to move it up to here. So we almost have to picture where the +4 line would be and then extend that in a different direction. And in fact, this would be the same thing if we changed our theta to 150. Then this would just be 4 units from that. So you notice that's a +4. That's because it's all attached to the angle at which we went. If I went from a -30 in this direction, but I want to be up here, then I need to go in a -r direction. So extending that same line that you would have had with +4 in the other direction. Okay, so let's take a look at an example of different ways that we could write, arriving basically at the same point. So we've plotted out this point that's at 225 degrees with a r value of 3, a distance of 3 from here. So we went 225. We know that this is 100. This is 45 degrees, right in between both the x-axis here on the left and the y-axis going down. And so we're going right in between those two. We want to do 3 more points, or describe this in 3 different ways. The first says we want our r to be negative and for our angle to be positive, basically between 0 and 360. So the only other way I could describe this angle, if we want to keep it positive, because we could also go in the opposite direction, right? We could go down. But since we want it to be between 0 and 360, the only other choice we have really is to go this way 180 degree, make this a straight line. And we know that this would give us 45 degrees. But we would want it to go in the opposite direction of this line, right? So this here would be 3 at 45 degrees, but that's not the same point, right? So to get to this point down here, I simply would need to make my r negative. So this would be -3 and positive 45 degrees. We go 45 degrees, but then we go in the opposite direction to get me down here. This gives me a -r with a positive degree between 0 and 360. Now let's do the next one. Here we also want to have our r be negative, but we want our angle to be negative, basically going from 0 or from -360 all the way up to 0. So my r has to be negative and my angle has to be negative. This is kind of like what we were looking at before. We know that the r is going to be -3, so it needs to go in the opposite direction of the angle that we put here. Let's draw this line back in, since we're still going to go off this. I need to describe this same angle, but in a negative way. And let's put our point up here. This would be positive 3, because we're going to describe the angle here, but we're going to use a negative angle. So to get to there with a negative angle, I basically need to come up this way. And with this angle being 45 degrees, I have to describe that. I have to subtract that from 360. So this would be negative 315 degrees. That would be this spot right here. Right? But we want it to be this point, the black point, right? So if we put that same degree in there, negative 315 degrees, and always remember to put that little degree there, that would take us in the opposite direction than this positive 3. We measure this out as being 3 units, but negative 3 would take us down to here. And so, yes, this is another way to describe positive 3 to 25, is to have negative 3 and negative 315. And then for the last one, we want a positive r. So we know we have to have positive 3 here, and we need to figure out what angle we want. Our angle needs to be negative, so I'm going to switch colors here and put that negative here. If I go in a negative direction, I can go straight to this line. So I'm describing the actual line, not its 180 degree extension. This is going to be 90 plus another 45. So that's negative 135. So with positive 3, I can put negative 135 here. That's the direction I'm going. And then from that line, we're going to go out 3 units. And that would describe that point there. So let's picture this within the polar coordinate system. I kind of did that when I was drawing out those last things, but let's put some symbols to it. As you see that this point here, P, if we attach it at the XY coordinate plane there, where they meet the origin, and we rotate it theta degrees, and we go out r degrees, this produces a triangle. It has a height of y and a distance, a horizontal distance of x. And these meet at a 90-degree angle. So letting the x-axis of the rectangular coordinate system serve as our polar axis, and the origin serving as the pole for the polar coordinate system, then each point has both polar coordinates, or we can express it this way, or we can express it this way. As you might guess then, there's a connection. There are connections we can make. Notice that R becomes the hypothesis of that triangle that's created, triangle that's created. And so we can make a bridge between both of these systems. And we'll do that here on the next page. Here are our relationships. Number one, we know that we've got a right triangle here. And so we have, as you guys are familiar, the ability to use the Pythagorean theorem there where x is one side, y is the other side, the two legs of the 90-degree angle of our right triangle, and r is the hypotenuse. And so x squared plus y squared we know is equal to r squared. But notice r is a part of the polar coordinate system there. Also, the angle that we have has a tie to the triangle as well. And with r and theta, we see theta here can be described using and can take us back to the rectangular system. Sine is opposite over hypotenuse, so y over r. Cosine is x over r, and tangent is y over x. So we're going to use these formulas to tie between the two systems and to allow us to convert. In fact, we can look at a connection right here. With this equation that we're given, if I cleared out my r, we have a relationship r sine theta. Notice that this side over here involves both r and theta, the two parts of the polar coordinate system, and we know that that attaches us to y, or would leave us with y on the other side with r canceling out. Same with what we have here. So we have x being equal to r times the cosine of theta, and we remember that cosine deals with x, and sine deals with the y. And with tangent here, we can do the same thing. So y, we know, is tied to x and tangent of theta. The two main conversion things we can use here, though, are these two. In fact, to convert the polar coordinates r theta of a point to rectangular coordinates, x, y, we're going to use these equations. X is equal to r cosine theta, and y is equal to r sine of theta. And it's easy to remember these because we've over the last few weeks have kind of pounded it into our minds that r is the x coordinate and sine is the y coordinate. So let's do some conversions. I'm going to draw this out too, just so that we can have a visual of this. So we're going negative 30 degrees, and we've got a distance of 2. So here is where it would be. This is negative 30. That took us in a clockwise direction. And so we want to convert this into rectangular coordinates. Well, to find the x, I'm going to take my r and multiply it by the cosine of negative 30. The r here, of course, I'll just go ahead and put this in. I probably could have put it in at the beginning here, but this would be 2 times the cosine of negative 30. Now, negative 30 is the direction. Doesn't mean my cosine is going to be negative. In fact, cosine, my x, will be positive, as we see here. And so 30 degrees for cosine is root 2 over 2. That leaves me with, root 3 over 2. Not root 2 over 2. That would be 45 degrees. So we get just the square root of 3 there. With the 2's canceling out, we think of this 2 as being in the numerator. And then for y, we're going to take 2 and multiply it by the sine of negative 30. And at negative 30, sine is equal to negative 1/2. 2's cancel, and we get negative 1. So, with a hypotenuse length of 2, what we see for x is the square root of 3, and what we see for y is negative 1. And so the rectangular coordinate for 2 and negative 30 degrees is root 3 and 1. Now, if we were doing tangent, if you recall, not 1, negative 1. Tangent is y over x. So this would be negative 1 over square root of 3. And that gives us our negative root 3 over 3 that we typically write for tangent. This is tangent of 30 degrees. Negative 30. And tangent is negative in the fourth and the second quadrants where x and y have opposite signs. And it's positive here and here where they're both positive or they're both negative, because negative divided by negative gives me positive. All right, let's go to the next one. We have -4 and pi over 3. Oh, they're giving it to us in a radian, throwing us off a little bit. But pi over 3 we know is 60 degrees. So that would take us up to here. But we're going in a negative direction. So -4 is actually out here. This would be +4, 4, and pi over 3. Oops. 4 and pi over 3. But the point we're really after here is in quadrant 3. This is -4 if we use positive pi over 3. So that's actually in the second quadrant. I'm sorry, the third quadrant, not the first. So let's start out getting our x's here. X is equal to r times the cosine of pi over 3. R is negative in this case, so we have -4 times the cosine of pi over 3. Cosine of pi over 3 is 1/2. And even though our actual point is in the third quadrant, we are using pi over 3. And so we want that to be positive 1/2. That is, we want to keep our eye on what's in front of us. So this is going to result in -2. Whoa. And that's our x-coordinate, -2, which we can label here. We can see that's taking us in the right direction. The y value is going to be -4 times the sine of pi over 3. And of course, the sine of pi over 3 is √3 over 2. And it's positive. We're dealing with pi over 3, not 4 pi over 3, which would be the angle if we're using a more direct method. So this leaves me with -2 square roots of 3. That's taking us in the proper direction. If we want to describe this from a rectangular point of view. Now the direct angle there is 4 pi over 3. So let's see what happens if I had done it from this. These two represent the same point. Pi over 3 with a -4, 4 pi over 3 with a +4. Using my x, that's +4 times 4 pi over 3, which is -1/2. And so that negative switches over to the angle, and we end up with -2, just like we had with the previous. +4 times -square root of 3 over 2 also leaves me with -2 square roots of 2. So we end up with the same rectangular point for both of these. That -4 is just telling us that once we've gone pi over 3, we're going to switch that 180 degrees and draw that line there. Now let's go in the opposite direction. Let's convert from polar or rectangular to polar coordinates. So if it's a rectangular that we're given an x and a y of a point to polar coordinates. If we're going to convert this, we're going to first find the quadrant in which xy lies. We can figure that out just looking at the signs of x and y. And then we're going to find r, and we're going to use the relationship between x and y and r, with r being the square root of the sum of the squares. 3, we're going to find the reference angle, theta prime. Now remember, when we do arctan and we do arc anything, we only have two quadrants in which we're going to arrive. And so basically this point is always going to give us we're going to take the absolute value of y over x, and we're going to do the arctan on that. And then look at where the quadrant is. Now, the reason we want to take the absolute value, why do we want to do that? We don't really want to do the negative. With tangent, tangent is, we express the positive here and the negative here. Because tangent is negative in both the second and the fourth, but like sine, we're only going to go from negative pi over 2 to positive pi over 2 in describing the outcome of an arctan. And so really we just want to reference it to the first quadrant and then build upon that. So let's take a look here at an example. The polar coordinates are theta of the point P, with r being positive and theta being between 0 and 2 pi, whose rectangular coordinates are negative 2 and 2 root 3. Negative 2 and 2 root 3. The point lies in quadrant 2 with x equaling negative 2 and y equaling 2 root 3. We can draw that out, right? This is simply our regular way that we've done this. Negative 2 takes me to here, and then if we go up 2 and a little bit more, we're way up here. So, the first thing we want to do, since we know we're in quadrant 2, is to find r. R we know is going to be the square root of our two numbers that are squared. We're squaring negative 2, and we're squaring 2 square roots of 3. That's our x and our y. So this becomes positive 4 plus this 2 squared applies to the 2 and to the square root of 3, so we get 2 squared, which is 4. Square root of 3 squared is just 3. So we get 4 plus 12, which is the square root of 16, which is, in this case, 4. So our R value is 4. We're going to end up, you'll notice in this formula, we're not taking the positive and negative, we're just taking the positive. So we're building this based on R being positive in this case. So we have our first of the two, 4, and now we need to find theta. So we'll go to step 3. We're going to find the reference angle. So what that angle would be in the first quadrant. So we're going to take the arctan of 2, root of 3 over 2. That's my y over my x. That negative, of course, goes away and cancels out, right? Because we took the absolute value of it, and the 2 cancels out. We just have the tan of positive square root of 3. And that gives me pi over 3. But the point P is in quadrant 2. So if we're sticking with 4 as my R, so positive 4, that means we're not going in the opposite 180 degree direction. We want to describe what pi over 3 would be in the second quadrant. Well, pi over 3 in the second quadrant is 2 pi over 3. It's 1 less than 3 pi over 3. And really, pi over 3 is 60, so that would be 120. That gives me 60 degrees to the x-axis there. That would be my polar coordinate for the polar coordinate expression of negative 2, comma, 2 square roots of 3. So now we're going to look at converting equations between rectangular and polar forms. As you guys have done throughout algebra, it has almost always had some sort of equation, relationship between x and y. We know that, for example, y equal to x squared. We can picture that on the x squared, not y squared. as a parabola. That's the pattern that emerges as x goes from negative to positive. It starts going up on both sides there. Well, we can do the same thing with polar coordinates, because here we're just expressing it as an angle and as a value for r. And then we're plotting it as such, where r is the distance and theta is the angle at which we're going to be spread or distanced out from the origin. And so we have a host of different, these are just examples of different types of equations that can be set up. I could also go like r is equal to 2 theta, right? There would be a unique equation that would result from that. So there's lots of different equations. We're going to look at some of them and some of their graphs that we get. But basically, how would we go from one to another? Well, let's remember the relationships between x. X is equal to r cosine theta, and y is equal to r sine theta. And if we remember that, there we go. We just have to do some substitutions, and we can look at what these equations would look like in polar form or vice versa. So let's do some converting. So x minus 1 squared plus y plus 1 squared equal to 2. We're going to convert that into polar form. Now let's take a look at this graph, because I want us to remember what this is. The general thing was x minus h squared plus y minus k squared equal to r squared. And so with this, h and k tell us the location of the center of the circle that's produced. And h and k will be opposite the plus or minus that you see, because we have that minus in front of h, minus in front of k. So x minus 1 actually has an h value of 1, and y plus 1 actually has an h value of k value of negative 1. So at 1, negative 1, this is the center of the circle. So that dot I drew is not actually a part of the graph. It's just going to be my reference point here. And the radius of this circle would be the square root of r there, so the square root of 2, which the square root of 2 is a little bit more than 1. So just going out a little bit more than 1 in every direction here, this would be the graph that we're talking about, though this is looking a little bit more like an ellipse. But I think that's just where I ended up placing my values of 1 there. So this gives me, actually it's supposed to be a circle, so use your brain to sort of visualize that. Well, let's convert this into polar form. All this is just me trying to remind you about the circle. Okay, so the first thing we're going to do is we're going to substitute r in for x. The r, we know that x is equal to r cosine theta, and y is equal to r sine theta. So plug it in. We're going to put r cosine theta in for x. So we have r cosine theta minus 1 squared plus r sine theta in for y plus 1 squared equaling 2. Those are the only things that we have to substitute. We have to get out the x and get out the y. Now let's simplify this out and see if we can combine some stuff together, maybe get the r's together. We'll see what we can do. So I'm going to square this. This will give me r squared cosine squared theta plus, or actually this would be minus 2, and then we take the product of these two. So we end up going -1 times r cosine theta, and we get another -1 times r cosine theta. So we end up with 2 r cosine thetas, and then we have -1 times -1, which gives me +1. Similarly over here, except that we have sine, we end up with r squared sine squared theta. Then we end up with the middle term, which is going to be the product of these two things doubled. So +2, 1 times r sine theta, of course, is just r sine theta. So we have 2 r sine thetas. And then we have +1 times +1, or +1 squared. This is equal to 2. Now we've expanded this out, and I want us to think in terms of what we're looking to do here is to get this to a polar equation. And a polar equation has the r on one side and the thetas on the other side. So that's kind of my goal here. I'm trying to keep in mind. So first off, what I'm going to do here is to group my cosine squared and sine squared. It's kind of get those written. I'm just going to rearrange things a little bit here. So first I'm going to put r squared cosine squared theta. We'll put those first. And then we have plus r squared sine squared theta. And then I'm going to get the cosines and the sines to the first power by themselves. So we had +2. I'm just going to put the +2r sine theta first, and then write -2r cosine theta. And then we had 2 +1s, so we're going to combine those and put +2. And then we have this equal to 2. Well, okay. Let's just go ahead and get rid of the 2 here by subtracting it and setting this equal to 0. If we have +2 and then we have 2 on the other side, those just kind of negate themselves out. So that just gives me something that's equal to 0. So I've simplified it. And with my cosine and sine, we're going to do a little magic trick here. They both have an r squared in front of it. So let's factor that out. So this gives me cosine squared. My pen's not working all of a sudden. Cosine theta. So it's cosine square theta plus sine squared theta. And I did that because cosine plus sine squared, this is going to simplify that quite a bit. We can also factor out a 2 and an r here. So plus 2r sine theta minus cosine theta equaling 0. And we'll see if that's necessary here. But cosine squared plus sine squared theta is 1, right? We like that. That's so great. That gets rid of it, so we just have r squared times 1, or r squared plus, I'm going to actually redistribute this here. I don't think we need to factor that out. So I'm just going to leave that as 2r sine theta minus 2r cosine theta. With this, and the reason I distributed it back is just so we could see that r is present in each product there. R is present in the 3 terms we have left here. So I'm going to factor out r, and that leaves me with r plus 2 sine theta minus 2 cosine theta equal to 0. Remember when we have something equal to 0 and we have a product, so I have here and here, we can break it apart and write it as two different, the solutions are the two different things. So r equal to 0 is one of the solutions, and then r equal to I'm sorry, not r equal to. This is equal to 0, and then the other one is equal to 0, so r plus 2 sine theta minus 2 cosine theta. Let's get rid of that underline there. That part of the parenthesis is equal to 0 as well. So we set them both equal to 0. And that is our solutions. Now, we actually don't need the r equal to 0 because this wouldn't give us anything in particular, r equal to 0. That would just be a blank x and y coordinate plane. So we can ignore that because that solution of 0 is also contained in this second one. If theta was equal to pi over 4, if we plug that in, that would give me 2 root 2 over 2 minus 2 times root 2 over 2, which results in 0. So that 0 is contained in what I have here for one of the possibilities for theta. So in other words, we're just going to ignore that. And C, remember, our ultimate goal is to get r and theta on opposite sides of the equation. So we have an equation that's relating. We like for a lot of our equations, we like to have it solved for r, like r equals 3x plus 2. We like to get all of the other stuff. What we're going to do is get r to the other side, but we want it to be positive, which means I'm going to subtract 2 sine theta and add 2 cosine theta. And that actually is, with r by itself, the equation that we are after. So we end up with minus, so let's put cosine first. Since it's being added, we'll like to not have the negative out front if we can avoid it. 2 cosine theta minus 2 sine theta. I subtracted sine and I added cosine. This is the equation solved and put into polar form from here to here. Notice that this here is akin to the radius that I had there. Well, the square root of that was. Anyhow, that's just looking for some patterns there. But this would give us the same graph. If we plotted out every possible theta, we would get the same graph that we have there, square root of 2, with the radius. Now, going the other direction is going to require some creativity, but we're still going to use our basic relationships that we've laid out here, where r squared is equal to x squared plus y squared. We just want to keep all these in mind. How do we go from one to the other? Okay. For example, this is going to help us, this relationship here with theta, it's going to help us figure out what y and x are. So let's look at an example. We're going to go from polar to rectangular. We're going to start with just r equal to 3. So this is a polar equation where r is equal to a constant. We just have a circle that's centered at 0 here. If we want it centered elsewhere, then we gotta do some more things here. But with r equal to 3, this is the graph that you would get, a circle centered at the origin with a radius of 3. Okay, looking back, let's think, well, where can we get some relationships here? We know r squared is equal to x squared plus y squared. We know that r cosine theta is equal to x, and r sine theta is equal, but we don't have a theta to work with here. So we need to be creative. So where will that creativity take us? Well, keep in mind, this is an equation. We have r equal to 3. That's one side. There's two sides to our equal sign there. We know that r squared is equal to x squared plus y squared. So one thing that I can do is say, well, let's multiply both sides by r so that it's at least looking like what I have there. Sorry, not multiply both sides by r. We're going to square both sides. Yeah. I mean, r times r would give us r squared, but that would give us 3r, which we don't want that. I'm just going to square both sides of this equation. This gives me r squared on the left, but then it gives me something much simpler, just 9 over here. So we have r squared and we have 9. And now we have a bridge to take us to x and y. Instead of r squared, I can actually just stick in x squared plus y squared equals 9. This also is the formula, the xy coordinate system formula for a circle, where the radius, we think of this as r squared, the radius is 3. And so we've converted it. And there wasn't a direct substitution, right? Here what I had to do was to get it somewhere where we could substitute. I needed to be able to substitute. We knew that r was equal to the square root of x squared plus y squared. So we could have put that in there and then squared both sides to get rid of the square root. And that would have taken us to the same spot. Let's look at another example. On this next example, we have theta equals 45 degrees. And this is what we get. This is for any r. So r is anything we want it to be. We just get a line that is 45 degrees lifted from there, from our starting point. Let's look again at what we might be able to do. We have a theta, and we're told that, and remember, we're trying to take this to, we don't have an r, so there's nothing I can do to, substitute out the r, but I know that the tangent of theta is equal to y over x. And so going to our problem here, let's try taking the tangent of theta on both sides. So that would give me tangent theta on the left, tangent 45 degrees on the right, and we can carry that out. Tangent of 45 degrees is 1, so now I have tan theta is equal to 1. Now remember, our goal is to get this in terms of x and y. Well, we do have a relationship there now. Because I took the tan on both sides, now I have something I can substitute out, because we know that the tangent of theta is equal to y over x. So this can be substituted. We're finally getting to a place where we can put it in terms of x and y. This is equal to 1. And then I can multiply, get these on opposite sides, and we see y equal to x is the rectangular equation for this same graph, where theta is equal to 45 degrees. When x is 1, y is 1. When x is 2, y is 2. X is 3, y is 3, right? That gives us a line, -1, -1, -2, -2, -3, -3. That's the line we get for y equal to x. It's a line with a slope of 1 that crosses through the origin, y equals mx plus b. So since we don't have a b, we assume that b is actually a 0. So that's our y-intercept. Okay, r equal to cosecant of theta. I'm going to rewrite this because we don't have anything dealing with cosecant, but we do know that cosecant is 1 over sine theta. And if I multiply both sides by sine theta, I end up with 1 over here. And the reason I'm doing that is because I know that r times the sine of theta is something. R sine theta equal to 1. Well, we know r sine theta is y, right? That was one of our relationships. We have x equal to r cosine theta, and y is equal to r sine theta. So I knew those two relationships. So if I replace that, I have y is equal to 1. And this is actually the graph we get with y equal to a constant. In polar form, this is r equal to cosine theta, or cosecant theta. Whatever we plug in for theta, we're going to get r. Remember, it's an angle and r. So it happens to be that when we have cosecant of theta, whatever theta I put in there, it'll be equal to the r will equal that. And we end up getting y equal to 1 for that. For r equal to 2 cosine theta, this is the graph we get. It's centered at 1, 0, and we end up getting a circle around that point. So here we're actually given a theta and we're given an r. We want to look for a way to make this into x and y. So let's look back again and see if we can maybe draw some inspiration from what we have. Let me write down what we have. We had r equal to 2 cosine theta, and we want to convert all of our thetas and r's to x's and y's. So we want to get rid of them in one foul swoop if we can. Now, we do have r cosine, and we know that is equal to x, but here I have 2 cosine, so I can't just do that. And we also need an r squared to, put in x squared plus y squared. So maybe I can introduce an r on both sides and knock this out in one foul swoop. Let's go back to our page that we had. So instead of just doing a direct substitution from the beginning, if I multiply both sides by an r, this gives me r squared on the left and gives me 2r cosine theta on the right. And there we can do some substitution. This is equal to x. X is equal to r cosine theta. So I have 2 times x here, and I can put x squared plus y squared here. And so that's 2x. I can subtract that to the other side, equal to 0. X squared minus 2x, so subtracting that. And we have plus y squared. This is looking, and we know we're after a circle here as we're looking at it. If I have this x squared minus 2x, I'm going to want to factor that. And so I can complete the square by taking half of what I have here. So half of negative 2. So 1/2 of negative 2. If you guys remember this procedure is negative 1, and we square that. So we take 1/2 of b squared, we get 1. If I add that to both sides, I can do that. I can add whatever I want to both sides. This gives me a perfect square trinomial involving the x. Oops. Which can be factored. This would factor 2 x minus 1 squared. Then we have plus y squared equaling 1. This is fitting into my x squared plus y squared equal to r squared. My r is the square root of 1, which is 1. You can see that's the radius that we have, 1 to 0 and 1 to 2. That's a distance of 1. So that's my radius. And x minus 1 means h's value is 1, right? The opposite of what we see. We just have y squared, so that's like y minus 0 squared. So it's centered. My hk is at 1, 0. So here I have done it. Now, a lot of times I know we like to express this in terms of x and y, but with circles we tend to have them in the form x minus h squared plus y minus k squared equal to r squared, simply because it tells us where the center of the circle is, which is really necessary for us to graph. The center is always at hk. So there we had it. We just want to use our creativity there to try to do some substitutions. And with a little perseverance, we've done that. This should get you started on today's assignment, practicing all the things we've done here. We'll see you on the next one.